Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. This series is Individual and Social Choice. We're now in the fifth installment of the series. I can't stop talking about preference, choice, and utility. Last time I went super long, and I guess I just need to finish that. I'm going to call this, I'm running out of titles here. Let me call this one, this installment will be more on choice and utility. Continued, I guess. Yeah. More on choice and utility continued. Okay. So where we stopped last time was in the proof of this proposition. Again, utility representation, it's an assignment of numbers such that more preferred alternatives have higher numbers. We work with utility representations a lot, even though they don't really add anything to they don't add anything substantial to the binary comparisons in the strict preference relation. They can be useful for describing preference relations and just for working with them, because we can use all kinds of techniques, like calculus and real analysis. So it's important to understand when a preference relation has a utility representation. This proposition, for the case of a finite number of alternatives, gives us a complete understanding, and it just boils down to preferences being a weak order. Okay, so because this is an if and only if, you can think of it as just two logical conditional statements. Last time we proved if P has a utility representation, then it's a weak order. So we proved the left to right direction, and what we have to prove now is the right to left. And this one, the first direction did not use the assumption that X is finite, but we will now. All right, so now the antecedent is that P is a weak order. So it's asymmetric and negatively transitive. We're assuming the set of alternatives is finite here. I'm not going to write it down again, but we're assuming that. And then we need to show that it has a utility representation. Another way of saying that is there exists a utility representation. So I used the term existence result when we were talking about maximal elements. Here we actually have to prove an existence result. Right? We're assuming P is a weak order. We have to show that there exists a utility representation. All right. How do you prove an existence result? Well, there's different ways of doing it. Here we're going to do it by construction, which means I'm actually going to present a utility representation. Okay. So how am I going to do that? Well, we're going to define a function. The domain of the function is going to be the set of alternatives, right? So you plug in an alternative, and it's going to give us back a number. And I'm going to describe how to, how that's defined right now. How do you go about defining a function like this? Well, you just need to assign a number to every element of the domain. In this case, we need to assign a utility to every alternative. All right, so what I'm going to do is I'm going to use some set theory here. So basically, I want to look at the set of alternatives that are worse than x. How am I going to describe that formally? Well, I'm going to use this curly brace notation for a set, and I'm looking for the alternatives that are worse than x. So for a generic alternative here, I'll call it y. I don't want to use x because I'm already using x. X is a, here I'm taking an alternative x. Now I'm going to form the set of y alternatives such that y is worse than x. Okay, so this notation here, this vertical bar, I'll read that as such that basically with this notation, I'm just, after that vertical bar, I'm giving a property that's going to isolate elements of the set that I want. Okay, what's the property? The property is that x is better than y. This is going to consist of any alternative that satisfies that property. So this is going to be everything below x in the ranking. Okay, you can think about it like that. Now, hold on a minute. That's a set of alternatives. The utility function has to assign a number to x. So what I'm going to do is I'm going to use the fact that the set of alternatives is finite, which means that I can count the number of elements in that set. I can count the alternatives below x in the ranking. That is a number. I should say, if x is the lowest ranked alternative in the ranking, there won't be anything underneath it. In that case, the set here we would call empty because there would not be anything in there, right? If x is the worst alternative, then there's nothing worse than x. So it might be that this set has no elements, in which case the utility is just going to be a 0. So in fact, let's go back to our example just to see what it would be like, what this utility function would be. So if A is above B and C and those are above D and E, then this utility function would be defined like so. There are 4 alternatives below A in this ranking. There's 2 below B, and there's 2 below C, and there's none below D and E. Okay, so this is the function I'm defining. And you can probably see, just intuitively, if an alternative is higher in the ranking, there's going to be more alternatives that are below it. So it should be pretty not surprising that this function is a valid utility representation. It's assigning a bigger number to alternatives that are higher in the ranking, right? So, but in an actual, in a proof, in a formal proof, you can't just say, well, it's obvious intuitively. You actually have to show it. So given this utility, I don't know it's a utility function yet. I have to prove it. So given this function, I need to show what? Well, what's the defining property of a utility function? I need to show that for all alternatives, x and y, that that x is better than y if and only if it has a higher number. Okay, so what I'm going to do is I'm going to consider any alternatives A and B. Now, when I pull them out of the bag, I like to give them, names like A, B, and C. All right, so we need to show if x, sorry, need to show that A is better than B if and only if it has a higher utility. And of course that, well, let me just rewrite that. That's the same thing as saying that there's more alternatives below A than there are alternatives below B. All right, so I have my two alternatives, A and B. I need to show that this property holds, okay? Notice here we have again a biconditional statement that you can think of as just two conditional statements, a right to left and a left to right. So, you know, as we're getting into this proof, it's like, you know, layer after layer, and, you know, you can, you know, proofs can be very complex. You can, you know, here I'm to prove a biconditional statement, I end up having to prove another biconditional statement, and, you know, it could go on from there. But this is as far as we'll go with the biconditionals. All right, so first let's show the left to right direction, okay? So first, let's suppose that A is strictly better than B. We need to show that there are more elements that are worse than A than there are elements worse than B. How am I going to do that? Well, there's going to be two steps. So the first step is going to be to argue that any element, step one, I'm going to show that if B is better than Y, then A is also better than Y. Okay, so anything worse than B is worse than Y. This is step one. Well, that's actually pretty quick work, right? If well, if B is better than Y, then, well, we're assuming that A is better than B. B is better than Y. Because B is since P is a weak order, it's transitive. So that tells us that A is better than Y. Okay, so anything that's worse than B is also worse than A. In set theoretic terms, this means that the set of things that are worse than B is a subset of the set of things that are worse than A, right? Any Y that's worse than B is also worse than A. And the way we describe that is with this, this notation here that's a little bit like a curvy inequality, but this just means all the elements of the set on the left are contained in the set on the right, okay? So right away, that tells us that the set on the left cannot be bigger than the one on the right. If the set of things that are worse than B is contained in the set of things that are worse than A, then we have to have this inequality, okay? But that's not quite what we need to show, all right? What we need to show is that if A is preferred to B, then there's strictly more things that are worse than A, okay? So we're almost there. We've shown that the set of things worse than B is contained in the set of things worse than A. Now we just have to show that there's at least one extra thing worse than A, right? We have to show that, let me just go down to the next slide. So then it suffices to find an alternative that's worse than A, but not worse than B, right? Going back here, right? We have the set inclusion, which tells us the set of things worse than B cannot be bigger than the set of things worse than Y. Now we just need to find an extra element over here in that set to make it strictly bigger. All right, anyways. So, but that's actually really easy. Note that, well, A is strictly better than B. We're assuming that here. So that means that B belongs to the set of things that are worse than A. But B is not worse than itself. The way we write that is this element sign with a slash through it. So that gives us something worse than A that's not worse than B, and thus we get the inequality we wanted finally. The set of things that are worse than A actually has to be strictly bigger than the set of things that are worse than B. All right, that tells us if A is strictly preferred to B, then it has a higher number assigned by this function, okay? All right, so, but now we have to go back, right? Now we've done the left to right direction here, right? We show that if A is strictly preferred to B, then it has a higher number. Now we need to show the right to left, okay? So let's do step 2. Let's suppose that A has a higher number. Okay. We've defined this function. Suppose that the function gives A a higher number than B. Well, by construction, that means that the number of things worse than A is strictly bigger than the number of things worse than B. All right. So the first set is bigger than the second. Of course, that means that there's something in the first set that's not in the second. Okay, so let's call that C. So there's some alternative, let's just give the name C, such that C is in the first set, so it's worse than A. But it's not in the second set. Okay. Since the first set's strictly bigger than the second, that means it has to contain something that's not in the second one. All right, so, well, if C is in the first set, that means that it is worse than A. So A is better than C. Since C is not in the second set, that means that it's not worse than B. But that means that C is at least as good as B. Okay, just by definition of weak preference. Now let's hook these two things up here. So that means we have A strictly better than C, C at least as good as B. Now if you remember the ranking theorem, there were two parts to the ranking theorem. I believe this was the first one. If one alternative is strictly better than the second, and the second is at least as good as the third, then the first is strictly better than the third. So let me just write by the ranking theorem. The first is strictly better than the third. And that's what we needed to get, right? We took two alternatives, A and B, where A had a higher number according to the function we defined. Turns out that's only possible if A is strictly preferred to B. That gives us the left and right directions. So we've proved this biconditional since A and B were arbitrary alternatives that I drew out of the bag, it follows that U is a utility representation of P. All we assumed there, well, we're assuming that the set of alternatives is finite. We assumed that P was a weak order, and we produced or constructed a utility representation of P. So, so that's a fairly long proof, but it's kind of a fundamental result in rational choice modeling. Basically, it means even if the set of alternatives is infinite, we're basically good to go and assume that if a decision maker, if their preferences are weak order, then they have a utility representation. Very last thing. So let's then go ahead and assume that P has a utility representation. Now remember, the optimality principle, the way we formulated it was that the decision maker will or should, depending on the use of the model, choose a maximal element from the set of feasible alternatives. Okay, so X is, let's say, a plausible choice. If and only if it's maximal in Y. With respect to P. Well, I just want to make the point that this is the same thing as saying that if we have this utility representation, I'm going to use U for that. If we have this utility representation, you can think about maximizing the utility representation here, though, because there's a feasible set Y, and those are the only alternatives available. We're going to restrict the maximization to this feasible set. So this is the problem of finding the alternatives in the feasible set that give the highest utility possible. Saying X is maximal is the same thing as saying that X solves this utility maximization problem. Those are the same things. In other words, we can write a biconditional between these two statements. Okay. This is a long way of saying that the optimality principle, we formalize that as in terms of maximality. That's the same thing as saying utility maximization. Okay, so in rational choice modeling, if you're working with a utility function, we assume that the decision makers choose alternatives that give the highest possible utility from anything that's feasible. Okay, so if you've heard of utility maximization but not maximality, that's fine. They're the same thing. Okay, that's it for now. In the next installment, we will be talking about having more than one decision maker. We'll assume we have a bunch of people. Each person has a ranking. How do they choose something collectively if they disagree about what the best choice is? And so this is called preference aggregation. We'll talk about majority voting, and things get more interesting from there. So that's it for now. I'll see you in the next one.